Okay, I think we better get going. So to everyone who's here, I'd like to welcome you to the next installment of QSI's online seminars. Today we have a very exciting talk by Professor Tom Stace. Tom is the Deputy Director of the ARC Centre of Excellence for Engineered Quantum Systems, and he's going to tell us about some really interesting recent work that he's done with colleagues all around the place, actually, into a more nuanced interpretation of what Transmons qubits look like. All right, thanks, Tom.
Thanks, Nathan, and thanks everyone who's joined in. I've got my participants list, so if you've got a question, there's a little button there you can press to raise your hand. There's a little blue flag next to your name so I can see if you've got a question, or type something in the chat window, which I can also see, or unmute yourself and just interject, and I'll answer questions as we go happily. So what I'm going to talk about today is well, what I've called as a new kind of qubit, and it's really a family of encodings that I think hasn't really been considered before, and so that's where I'd like to get to by the end, is to at least explain to you the much bigger state space that's available, particularly in superconducting devices. So I know that there are plenty of people at UTS who work on superconducting gadgets and have thought about them in theory at least. But for those who haven't, I'll give a quick review of what we mean by superconducting qubits. And the starting point for that is to think about Josephson junctions. They're one of the family of superconducting circuit elements like capacitors and inductors, and they're characterized by a very specific constitutive relationship, which is the top one there. That is that the Josephson current is a function of the flux linking the junction, and it's not just any function, it's a nonlinear function. It's a sinusoidal function of that flux. So they're interesting devices because they're extremely nonlinear. And so people have used Josephson junctions in all sorts of ways to fabricate really large nonlinearities in superconducting gadgets. So for our purposes, I'm going to think of the superconducting flux, the magnetic flux in the circuit is big phi, and I'm going to define this quantity little phi, which is a dimensionless form of big phi. So whenever you see little phi, you can think of it as an angle, a phase that sits inside a trigonometric function. But really what you should think of it as is a dimensionless form of a magnetic flux. And so given this constitutive relationship, you can go through canonical quantization and find a Hamiltonian that represents this sort of term in a circuit. And what you find is that the Hamiltonian for a Josephson junction is proportional to the cosine of the phase or the flux. So that's really the starting point. It's a Ginzburg-Landau mean field theory model, if you care about where it comes from. But I'm going to take that as the starting point for understanding Josephson junctions. So how do you make a superconducting qubit? Well, there's a whole zoology of superconducting qubits, and there's one continuum of such things, which range from things that are called Cooper pair boxes up to things that are called transmons. And they're parameterized by two numbers, EC and EJ. So you can recognize the second term here is a term associated to this Josephson junction. And the first term is a capacitive energy, EC times n squared, that's associated to this capacitor. So that Hamiltonian is the Hamiltonian for that circuit that I've just drawn there. And so in such a gadget, the main thing I want you to keep in mind is that n and phi just look like momentum and position respectively. So this is a thing which, if in a mechanical analogy, would look in this picture like a momentum term, p squared, minus some nonlinear function of the coordinate phi, or position, if you prefer to think in mechanical terms. So there's a very obvious symmetry in this Hamiltonian, that is this periodic 2 pi periodic term in phi, and that's going to have some significant consequences for the spectrum. There's a symmetry, and symmetries always lead to interesting phenomena in physics. But there's an important question. When I've written this Hamiltonian, I haven't told you what the domain of either the charge or the phase, the flux, is. And so that's a question that's almost never articulated in the literature. But it is an important question to answer before you start analysing this thing. You know, if you think about the usual canonical quantization method, you write down the coordinates you care about and define the Hilbert space on which they act, and then you can write Hamiltonians for those things. So I'm going to come back to that question repeatedly. What's the domain of phi? So the standard answer to that question, what's the domain of phi for these sorts of devices, is to say that phi is a compact coordinate. That is, it's an angle that goes from, say, minus pi to plus pi. And if you take that point of view, that's a very conventional point of view, what you find is a few conclusions that follow from it. So the first conclusion is that the charge, which is the Fourier transform, the charge operator n, which is a Fourier transform of the flux, is going to be discrete. So the spectrum of the charge is going to be a discrete coordinate. The other thing that you find is that it's very straightforward to diagonalize this Hamiltonian. And so I've plotted here the eigenspectrum of that Hamiltonian, assuming that the flux or the phase is a compact coordinate. And when you do that, it looks very familiar. There's a ground state, which looks a lot like a harmonic oscillator ground state, and then there are excited states sitting above that. And one of the things that you'll notice in that picture is that the eigenstates are discrete. That is, there's a discrete family of eigenstates of that Hamiltonian. There's a parameter that I haven't talked about yet, NB, which is a bias charge. So that's a parameter that typically is thought of in the context of this circuit as an external voltage that might be attached to here. So some sort of bias voltage attached via some capacitance. I haven't drawn that very well. Attached by some capacitance to the circuit, which lets one offset the charge by some amount that's controlled by that external voltage bias. So this parameter NB is conventionally thought of as a control parameter that's set by some external voltage. And so one can then analyze this Hamiltonian for different values of NB, and the spectrum that I've plotted here is for NB equals 0. So it's very symmetric. You can see the eigen spectrum. You can read off the eigen energies. There's an eigenstate with energy -1. There's another one with energy about √2 thereabouts. There's another one which has got an energy of about 2, and then unbound states up here, which look increasingly like free particles. And so as a function of that energy, this parameter NB, you can plot the eigenvalues for different values of NB. So at the bottom of the slide, you can see 3 different plots for different values of EJ, and it should really be EJ over EC. So these are all dimensionless quantities. And so if EJ over EC is very small, then this picture over here is what the spectrum looks like. At NB equals 0, you can see there's a lowest energy eigenstate here. There's a near degeneracy at this point here, and then there are higher excited states going up above those. And if I change NB by some amount, you can see that the energy of the ground state changes, the energy of the first excited state changes, the energy of the next excited, etc., change. And so I can plot this thing that looks like a spectrum, but it's really just a locus of the eigen values of that Hamiltonian as I change this parameter NB. So this limit over here is what gets called the Cooper pair box limit. It's a small value of EJ relative to EC. At an intermediate value here, you can see the spectrum looks qualitatively similar. There's a lowest energy state whose energy depends on NB. There's a next excited state, etc. And you can see that as I increase EJ, I get phenomena like anti-crossings here and anti-crossings at the edge of this picture. And then in the limit where EJ over EC is substantially larger than 1, then I get this sort of spectrum. And you can see that one of the characteristic features is that this lowest band and this first excited band have become much flatter. So if I took EJ over EC to be, say, 10, then the oscillation in those two spectral functions, this blue line and this orange line, would become smaller and smaller. And that is to say that the fluctuations of the energy with respect to this external voltage get smaller. And that's why people like transmons experimentally, is that they have a low susceptibility to fluctuations in external voltages. That is, no matter where you put this parameter NB, the energy of these two states is hardly changing with respect to NB. And so in transmons, the two states corresponding to the lowest energy in the first excited state are the states that people think about encoding quantum information in. Okay, so people build these gadgets. So here's a photo that I took from a talk of somebody from IBM, and I'm sure you've seen these kinds of pictures before. Here's a representation of a scanning electron microscope of a fabricated Josephson junction. These two metallic digits that extend vertically and horizontally in that picture overlap with each other, and the interface between them is a thin insulating barrier, and that thin insulating barrier permits tunneling of Cooper pairs, and that's how they form Josephson junctions. And the idea, as I just said, is to encode in that in the eigenstates of the lowest two eigenstates of that device. It's the same device here. It's an anharmonic oscillator. Encode in those two lowest energy eigenstates information that one might want to then process in a quantum computer. So that's the basis for the IBM quantum computer, and also the Google quantum computer and Rigetti, etc. So this talk's not really about understanding transmons that have been thought about for over a decade now, and in broad terms are well characterized, and people have fabricated them reliably. What I want to do is to take a step back and think about a bigger picture. But to do that, I want to show you this table which characterizes the sorts of circuit elements that exist. So there's two that you're extremely familiar with if you've ever thought about electronics or electrical circuits, which are linear elements that respond to either the flux or the charge. And those elements have names. So there's an inductor, which is a gadget whose current is proportional to the flux linking that gadget. There's a symbol for an inductor. And a capacitor, which is a device whose voltage is proportional to the charge that's crossed the device. And that gets called a capacitor. So there's this intrinsic duality, or this duality that exists between flux and charge, that if I relabel flux by charge and current by voltage, I map between inductors and capacitors. There are also nonlinear examples of at least inductor that are reasonably familiar, which is what I've just talked about, the Josephson junction. So the Josephson junction is a thing whose current is determined by the flux, but it's no longer a linear function of the flux. In fact, it's a sinusoidal function of the flux. And I've left this blank space here tellingly, because one might imagine that the duality between flux and charge should imply that there is an object, a physical object, that can be put into this quadrant. And that thing exists. It's called a quantum phase slip device. So it's a device whose voltage is a nonlinear function of the charge across it. So you should think of a quantum phase slip device as a nonlinear version of a capacitor, just as a Josephson junction is a nonlinear version of an inductor. And so now we've got four devices that we can think of building superconducting circuits with. And let me go through the zoology of some of the things that people have built. So if I put an linear inductor and a linear capacitor together, I get a very well understood object called a harmonic oscillator, an electrical harmonic oscillator. And you can think of that entirely by analogy with a mechanical oscillator, where the capacitance is now something like a mass and the inductance is something like a spring constant. And if I put them together, I get a characteristic frequency that's 1 over the square root of the inductance times the capacitance. So if I put a nonlinear inductive element, that's a Josephson junction together with a capacitor, then I get a whole family of devices which have been called superconducting qubits, and they include the transmon and the Cooper pair box. So that's this kind of device I showed you before, and they're characterized by having an anharmonic spectrum. And so that's very nice for building qubits, because then I can use frequency. I can tune the frequency of a microwave source to address specific transitions that I'm interested in, either for encoding information or perhaps for reading things out. So that's what I'm going to call a superconducting qubit. There's another thing that one can do, which is basically invoke the duality between flux and charge and put together an inductor with this dual nonlinear capacitor, quantum phase slip element. And what you end up with is a thing that's precisely dual to what I had just called the superconducting qubits, but I'm going to call it superconducting dual, superconducting star qubits. And people have built versions of those. I'm going to talk a little bit about that, but I don't want you to think that that's what I'm talking about when I say a new kind of qubit. This is just invoking a duality between flux and charge to come up with a new group of qubits, or a different group of qubits that people have started thinking about. So what is a quantum phase slip junction? Well, it's a thing that's characterized by whose voltage is a function of the charge, just like a capacitor, but by analogy with an inductor, with a Josephson junction, that relationship is not linear, it's sinusoidal. So the constitutive relationship for a quantum phase slip device is that the voltage is a sinusoidal function of the charge that's passed through the device over time. And before I go on, maybe I'll draw a little picture for that helps to describe the relationship between well, how one might build a quantum phase slip device. And let me draw this picture here. So what does a Josephson junction look like as in terms of the material properties? Well, a Josephson junction is a thing where I have two bits of metal with a superconducting gap between them, and electrons hop across that gap. That's a Josephson junction. A quantum phase slip device is a similar sort of thing, but now it's a piece of metal, the red means metal here, separating two bits of insulator. So in a Josephson junction, I've got two bits of metal separated by an insulator. In a QPS, I've got two bits of insulator. Maybe I'll draw the insulator in blue. Two bits of insulator separated by a piece of metal. And what is it that tunnels in that case? Well, it's flux. It's flux quanta. Josephson junctions, it's charge Cooper pairs, and in QPSs, it's flux quanta. So there's not just a mathematical duality, but there's some sort of physical duality that I replace insulators with metal and metal with insulator, and I map from a QPS to a Josephson junction and back. I'm also going to non-dimensionalize the charge in a quantum phase slip device, and I'll refer to that as the charge operator N. N is dimensionless. It's just the physical charge, the dimensional charge divided by 2e. And so if I write down this constitutive law for a quantum phase slip device, I can calculate an effective Hamiltonian that gives rise to that constitutive law, which is very analogous to the Josephson junction. It's just that the Hamiltonian is now a nonlinear function of the charge, that is, it's cos of the charge. So I can go through exactly the same kind of story with these dual superconducting qubits. I can put an inductor in parallel with a quantum phase slip device, and I end up with a thing that's precisely dual to the capacitor in parallel with a Josephson junction, and the Hamiltonian looks exactly dual as well. So now I've got a term that's like phi squared that comes from the inductor, and I've got a term that's cos 2 pi n that comes from the quantum phase slip device. And now, rather than thinking of the charge as a momentum, I'm going to think of the charge as a coordinate in a potential, and I'm going to think of the flux or the phase as the kinetic part. And the reason for doing that is that this is the quadratic term, so it looks a lot like p squared over 2m. So whenever I see something quadratic, I'm free to interpret that as the kinetic piece if I wish. And so what would this device do if I were to build it? Well, again, I have to ask the question, what's the Hilbert space on which these two operators phi and n act? And so by analogy with the Josephson junction, where I had a term which was cos, for the Josephson junction, I had a term that was EJ cos phi. And when I wrote such a thing down, I sort of made an assertion that because the term in the Hamiltonian was 2 pi periodic, therefore phi was a compact variable. I'm going to invoke the same, or the dual argument here, which I'll formalize a little bit later, to say that because this term cos 2 pi n is periodic, n is a variable that takes a compact domain, in this case -1/2 to +1/2. So it's got a domain that's interval length is 1. And if I do that, well, I end up with a Hamiltonian that's got a cosine potential, that's this term here, and I can diagonalize that Hamiltonian and come up with the eigenstates, and they look exactly the same as they did for the superconducting qubit for transmons or Cooper pair boxes. I've got a ground state that looks like a harmonic oscillator ground state, and I've got excited states that sit above that, and it's anharmonic, so the transition frequencies are anharmonic. And similarly, I can introduce now, I've got a parameter phi b, and this parameter phi b is dual to the voltage bias NB that I introduced for the transmon. It's just a parameter that's controlled by some external flux that I might have access to via some current bias. And if I plot now the energy eigenspectrum as a function of phi b, that's what I end up with here, for a small value of the ratio of the prefactors EQ over EL, I get a spectrum which has a characteristic form, a lot like the one I showed you before for transmons, for Cooper pair boxes, sorry, where I've got a lowest band of energies, a next band of energies, and a next locus of energies, should I say, of ground state, the first excited state, second excited state. And as I increase this parameter, this ratio EQ over EL, I end up with the same sort of characteristic behavior. That is, I end up with anti-crossings, and I end up with energies that are almost independent of the flux. So in this picture, I've named this end of the parameter space transmon star. That is, it's dual to the transmon in the sense of replacing charge with flux and flux with charge. And this end, by analogy with a Cooper pair box, I've called it a flux box. So that would be a thing in which the flux is a reasonable quantum number. And I can think of the eigenstates as being characterized by being in one or other flux state of the circuit. So that's a dual superconducting qubit. And again, I want to reiterate that's not the new kind of qubit that I'm talking about. There goes my daughter running through the lounge room. So the new kind of qubit that I want to talk about is the last combination that I can form between flux and charge devices in this table. So I'm going to take both nonlinear elements, the Josephson junction and a quantum phase slip junction, and put them together in a circuit. And that's the thing that I'm referring to as a new kind of qubit. And here's a picture of it. Quantum phase slip device and a Josephson junction in parallel. And that came out last year. You can look up that reference if you're interested. And we've called that, we've named that, that's one of the prerogatives of people when they come up with a new kind of qubit, and we've named it the dualmon. Yeah, I should take a straw poll if people like that name, but anyway, it's in the literature now, so it doesn't actually matter what you think. But here's the Hamiltonian for that Hamiltonian. It's for that device. It's made up of a nonlinear charge dependence and a nonlinear flux dependence or phase dependence. Cos 2 pi n and cos phi. So that's a sort of interesting Hamiltonian. And the reason I got interested in the first place in this was I had been thinking about quantum phase slip devices for a different application, and then started wondering idly, what happens if you put them together with a Josephson junction? Now, it turns out that Hamiltonian had been written down in abstract terms, in mechanical terms, X and P, in a paper by Kitaev and in some condensed matter literature previously. But it's not something that one typically sees. And the reason for that is that there's no natural kinetic term. So you can see that as a consequence of cosine being a bounded function of its variables, it doesn't matter whether if I take charge or flux to be compact or non-compact, cosine is a bounded operator. And so the maximum energy of this thing and the minimum energy of this thing are finite numbers. So that the spectrum of that Hamiltonian doesn't have it has a ground state, but it also has a maximally excited energy which is unusual. So typically when you think of any mechanical system, there's certainly a ground state, so there's a lower bound on the energy, but there's no upper bound on the allowed energy. And so in this case, it's not clear which thing you should think of as the kinetic term. There's no natural p squared like term, and which term you should think of as a potential term. But nonetheless, it's a Hamiltonian one can write down. Just to reiterate, phi and n mechanical like, there's an analogy with mechanical commutation relations, xp is IH bar, phi and n being dimensionless quantities. The right-hand side of their commutation relation is dimensionless, but it is of the same form. And so the question is, what are the properties of this device? And what I'll get to is that there's an interesting encoding for a qubit that sits inside that. But there's a problem with that Hamiltonian, which is that if I suppose that, like I did for the transmon, that the flux or the phase is a compact variable going from -pi to +pi, well, then I told you this in words, that there's the Fourier transform of that domain is the integers. And so the typical thing people will say is that the flux is the superconducting phase is a compact coordinate, and therefore the charge n is a discrete variable in that's characterized by the integers. And so if I have a charge operator n whose spectrum is the integers, then cos 2 pi n is equal to 1. So that's a statement independent of n, cos 2 pi n, the operator, this operator here will just equal 1 for all n in the integers. So that tells you that if I have this device and I assert that the flux or the phase is compact, then the cos 2 pi n term has to just be the identity. It's trivial. And so I may as well have not put the quantum phase device into the circuit in the first place and just had a Josephson junction sitting in isolation. That could be one conclusion. Another conclusion is, in fact, that my assumption that the superconducting phase is compact is false. That's the second point here, that the superconducting phase may not be a compact coordinate. That is, it could be the real numbers, in which case the Fourier transform is also the real numbers, and I would conclude the charge is not an integer. It's not in the set of integers. Its support is over the entire real numbers, and as a consequence, neither the flux nor the charge, or the phase and charge, are compact coordinates. And if that's true, then I shouldn't think of cos phi as a trigonometric function of a compact coordinate. I should think of it as a trigonometric function of a non-compact real number. And then instead of having discrete spectra, what I end up with is a band structure. So in that case, I can draw the band structure for the system. Now, thinking about this Hamiltonian down here, where phi is no longer a compact variable, it's now a real number. That is, it takes all the values along the real line, and as does the charge operator n. And I can plot the spectrum of that thing very straightforwardly just by taking one of the plots that I had earlier. I think this is for EJ over EC equals 2. I can plot that spectrum again, but I'm going to replace the parameter NB, which was a classical parameter, a classical voltage, with a new coordinate K, which is now a quantum number called a quasi-charge. So you'll need to think back to your Ashcroft and Merman to remember that when you have a periodic potential, the eigenstates are characterized by a quasi-momentum in that case. If the coordinate is a position, the dual quantity, the momentum, becomes a quantum number called a quasi-charge. And so this picture is exactly the same as I drew before. That is, the lines are all of the same form. But now, rather than thinking of this as a spectrum in which for each value of the horizontal axis I have a discrete spectrum, I should now think of this as characterizing the entire spectrum of the system. That is, K is a quantum number, and I can form states that live simultaneously on any one of these bands. So I've harped on a little bit about the structure of that Hamiltonian, but I want to describe a quasi-proof that this quantity phi is not a compact coordinate. And so I'm going to invoke a duality, so it's not a formal proof. It's not a formal proof, it's just relies on a statement about duality, but here it goes. So let's suppose that for this Hamiltonian, I've got a term cos phi, which is periodic, and I'm going to take that periodicity as the source of an implication that the spectrum of phi is periodic, or that phi is a periodic operator. That is, the spectrum of phi sits on a compact domain minus pi to pi. Cos phi is periodic, therefore, in this story, phi is itself a compact coordinate. It turns out by Fourier transform, this is what I've said before, the spectrum of the canonical conjugate variable n is the integers. So n is a discrete coordinate. Well, phi and 2 pi n have a duality in this Hamiltonian. So I'm going to invoke that duality and say, well, in that Hamiltonian that I wrote down for this new kind of qubit, cos 2 pi n is periodic, and by duality, that's going to imply that the spectrum of the charge is compact on the interval -1/2 to 1/2. And a consequence of that is that the spectrum of the flux or the phase is the integers, 2 pi times the integers. So phi is a discrete coordinate. So let me put these two lines together. Well, if the spectrum of phi, if I take the blue statements here, spectrum of phi is in the interval -pi to +pi, and the spectrum of phi is 2 pi z. Well, the only element in the union of in the intersection of those two sets is the number 0. 0 is both in this set and in this set, but there are no other numbers. And similarly, if I take the red statements, the spectrum of n is z, and the spectrum of n is in interval -1/2 to +1/2, then the intersection of those two sets is also 0. And so I see that the spectrum of phi and the spectrum of n must just be trivial. It's the set 0 for each of them. And if I have a degenerate spectrum like that, then the operators themselves are both the trivial operators 0, and then the commutator of those two things also must be 0. So that is a contradiction because I asserted back here that phi and n are canonical conjugate variables. So that's a quasi-proof that neither phi nor n are compact coordinates. In fact, both must be real. So if you take that seriously, what do you get? What does this system look like? Well, here I've got the circuit drawn again, a quantum phase slip device in parallel with the Josephson Junction. The Hamiltonian is this one that I wrote down. And one of the nice things about this Hamiltonian is that the two terms, the cos 2 pi n and the cos phi term, commute with each other. So this is something that's reasonably straightforward to check, even though phi and n don't commute with each other. Phi and n have the standard canonical commutation relation, but the cosine of those two coordinates does commute. And so what that tells you is that there's a symmetry, not just the periodicity of the phi and the n, but I can simultaneously diagonalize the charge and the flux terms in the Hamiltonian. And because they're periodic, I must therefore have two Bloch numbers that are associated to those to the eigenstates of that Hamiltonian. That is, I have not just a quasi-charge, but I also have a quasi-flux. And so what I can say for sure, without doing any analytical work, is that this Hamiltonian is going to be diagonalized by states that have two quantum numbers, k and phi, var phi. Var phi here is going to be a real number, and as is k. And I can write what those states look like in terms of the flux basis or the charge basis. The state k phi is just a comb of states, a sum of integers with weight sitting at 2 pi j in the flux basis, with a modulation that goes like the parameter k. And in the charge basis, it also looks like a comb at integer values of the charge. So let me show you what those look like schematically. So here's the k phi state. drawn schematically in the flux basis, it's a sum of states at integer multiples of 2 pi with an offset that's set by phi, and a phase modulation, which I haven't drawn, which is set by the parameter k. And in the charge basis, I have exactly the opposite properties. I have the charge state. It's a superposition of charge states offset by the integers with an offset of k. So they're two representations of the same state. I should have said this has got a modulation that goes like e to the I j phi. So they're two representations of precisely the same state in the flux basis or in the charge basis. And you can see that in both bases, they're these comb states. So I can, here's the Hamiltonian again for the circuit. And with a little bit of analytical work, it's straightforward to show that those states k phi, actually I'll write it back here, these states form a basis, and that basis is called the Zach basis. So it's a known basis of states, where one of the interesting things is that k and phi are each now compact variables. So k is in the interval -0.5 to +0.5, and phi is in the interval -pi to +pi. So even though the charge and the flux are not compact, the quasi charge and the quasi flux are compact coordinates. And so the energy of that system, it takes a little bit of work now, but you can calculate the energy of that system, and it's very simple. I replace the charge by the quasi charge and the flux by the quasi flux. This should be a var phi here, and that is the the set of eigenenergies of that Hamiltonian. And so I can plot them in this figure on the left. This is the contour plot of the spectrum. So you should think of an egg carton. So there's a minimum here at the middle, and there's a maximum at the corner. And so there's a trough that goes up to a maximum at this corner. And there are two other interesting points, which are these points here and here, which are saddle points. So the energy gets smaller going towards the middle, and it gets larger going up towards the corner for that saddle point, and the opposite case up here. So we have a spectrum which is characterized by these two quantum numbers k and phi. So maybe this is probably a good point to take any questions. Does anyone have any questions they'd like to ask at this stage? Looks like a no. Okay.
Actually, Tom,
oh, yeah.
while you're here,
Yeah.
You have this sort of quasi-proof that neither the charge nor the flux are compact variables. Does that only hold in the case of this particular type of device where you have a phase slip and a Josephson junction in parallel, or does it also carry across to, for example, Transmons qubits or other types of similar devices?
The short answer is yes, it does carry over to other devices. So let me give you the slightly longer answer, which is that if I write down a Hamiltonian, if I wonder if I can get a can I get a link?
You can do it through Zoom if you want. You can share
a whiteboard, I think.
You can do it in Zoom.
Yeah, that's okay. I'll just
pause. Just press W.
Is it W? Oh yeah, there we go. Yeah. So if I write down a Hamiltonian, which is a function of two operators n and phi, without specifying the contents of that Hamiltonian, that is the functional form of it, I should have already specified for you what the Hilbert space of n and phi are. So the choice of the Hilbert space for n and phi is primal, and the functional dependence of the Hamiltonian on n and phi is secondary. So how do I get back to that? Yeah. So how do I clear all that? Anyway, it's turned into a mess. That's right. So So the functional form of the Hamiltonian is independent of the Hilbert space on which n and phi act. And so I should have decided that up front. So all the point of that proof is that if I have a specific Hamiltonian and I had made the choice that n and or phi were compact, then I end up with this, this contradiction that is that both n and phi must be trivial commuting operators. So it's a specific, it's an instance of a Hamiltonian that fails to be interesting, or to have it fails in the sense that the commutation relations fail if I make a particular choice about the Hilbert space a priori.
Right.
And so when we come to talk about transmons, which I will do later, the same principle applies. I should choose the Hilbert space for n and phi before I start analysing the problem, which I'll do. So let me just sketch out some of the eigenstates. Were there any other questions?
Maybe I have a related question. So why does it matter to have a mathematical proof or quasi-proof of this fact?
Why does it matter?
Yeah, I think the best way to prove it is to build a device and like have the physics and have Hamiltonian measure things and see.
Sorry, I'm missing some of that. Can you speak louder?
So I was asking why a mathematical proof of this fact is really matter. Is it like to justify that this is a valid approach, or like you don't have physical realization yet? But like you do experiment and you see physics out of the experiment, you don't need any mathematical proof that is.
Well, okay. So the reason to give a quasi proof as I did is because the conventional wisdom, let's say, is that the superconducting phase is a compact coordinate. And so before one gets to do any experiments, you want to be somewhat persuasive that there's substance to the view that one's articulating. And so something that looks like a proof goes some way to doing that. But as you say, the truth of the matter is really an experimental question. And so one should come up with experiments that discriminate between the choice of the flux being compact or the phase being compact versus the phase being non-compact. And I will get to that later on. So there are distinct experimental consequences that flow from one choice or the other. Okay,
right, thanks, Tom.
Yep, you're welcome. So the spectrum, I've just reiterating here, it's this egg cup shaped thing with a minimum at the center and a maximum at the corner. And in this picture, remember that there's a periodicity that is this point. That is, this point up here and this point down here are the same, correspond to the same quantum state. But for each of these four red dots that I've marked, they're critical points on this spectrum where the gradient of the spectrum with respect to k and phi both vanish, are states that I can represent as eigenfunctions in either the phase or the charge basis, and I've chosen to represent them in the phase basis. So the central state, this lowest energy state, is a comb in the phase basis with comb lines at 2 pi multiples of the integers. And there's a uniformity to the comb, that is, every comb line has the same phase as its neighbor. The state that's here at this critical point, at this saddle point, looks similar. It's got comb lines that sit at every integer multiple of 2 pi, but now there's a relative phase of -1 between alternating states, between neighboring states. The state at the top saddle point is one in which I've got a phase offset of pi, but otherwise I have comb lines every 2 pi multiples of the integers. And then the last point, the maximally entangled state, maximally energetic state, is one in which I've also got comb lines at 2 pi multiples of the integers, but offset also by pi. So you can just look at those and do the integral in your head if you think of those spikes as delta functions, that they're all orthogonal to each other. And so it's an orthogonal, they're a subset of the continuum of the spectrum, and that particular subset is manifestly orthogonal. And they're also known as GKP code states. Gottesman-Kitaev-Preskill code states, which were thought about in the context of encoding qubits into oscillators. And it turns out that in this particular system, the Hamiltonian has those states as some of its family of eigenstates. Okay, so I've just described this new kind of qubit, this thing on the left, and if you're at all experimentally minded, you'll think, well, surely the story changes when you add realistic imperfections or parasitic capacitances, control voltages, inductances, etc. to the circuit. And so I want to, and noise as well. So I want to address those points reasonably quickly. I realize I'm running out of time somewhat. And I'm going to do that by thinking about two extensions of that circuit. So both extensions have a Josephson junction and a quantum phase slip device in the circuit. In one case, I'm going to add an external voltage that's going to model voltage noise or charge noise on that circuit. And in the other case, I'm going to add additional capacitances and inductance to model parasitic capacitance and inductance in the device. And in both B and C, I can then talk about how the system responds to noise or parasitic elements. So noise leads to decoherence. And so that's what I'd like to talk about for the model B, that is the one where I add an external voltage noise source. And I do that by including a term in the Hamiltonian, which is some charge noise, and another term which could be some flux noise that couples in via some spins or some external stray currents that live somewhere in the circuit. And this is the Hamiltonian for such a system that's coupled to both a voltage source and a flux, external flux and voltage. So now you should think of this nx and phi x as external parameters in the same way that nb was an external parameter previously. And this is the Hamiltonian that I now want to diagonalize, thinking about nx and phi x as potentially time-dependent external classical parameters. So I'm going to characterize the decoherence in the following way. I want to imagine that I can take any element in this spectrum, here, and superpose it with any other element. And in particular, I want to take the ground state, which is this k equals 0, phi equals 0 state. That's this central point here. That's this state. And I want to superpose it with any other state somewhere sitting on the energy landscape. And I want to ask, how long does that superposition survive for if I add some charge noise or add some flux noise? So why does noise give rise to decoherence? Well, I can think of those two states as having some energy. The ground state is the lowest energy, and this k phi state is some other energy. And if I let nx or phi x move by some amount, then both of those energies could change. Now, the ground state energy is a minimum. You can see from that contour diagram that it's a minimum. Locally looks quadratic. So small fluctuations in the charge or the quasi-charge have a quadratic effect on the energy of the lowest of the ground state. So it rejects noise at linear order. Other states, like the one here, for example, sit on some slope of the energy landscape. And so small changes in the charge or flux will lead to linear changes in the energy of that particular state. But there are other states than the ground state that have the property that the energy landscape vanishes. So this contour plot here is not just the energy landscape. In fact, it's the gradient of the energy landscape. It's the absolute value of the gradient of the landscape squared. And you can see that there are points where that gradient vanishes. Obviously, it vanishes at the ground state. It also vanishes at the maximally excited state by definition because it's maximally excited. And it also vanishes at these saddle points. That's the definition of a saddle point. They're points where the gradient vanishes even though it's not a local extremum. And so superpositions of the ground state with any of these other three critical states where the gradient of the energy landscape vanishes will have fluctuations in energy that are quadratic functions of charge fluctuations and flux fluctuations. That is, they reject noise at linear order. So there's a bit of maths behind this, but essentially the dephasing rate, gamma, of such states, superpositions of the ground state and any other state, go like sine squared of 2 pi k plus some constants times sine squared of phi, the quasi flux. And sine obviously vanishes at certain points, and that's where these red dots are. So the critical points in the energy landscape actually are decoherence free spaces in as much as they reject noise at linear order. So that's one extremely nice consequence of this this device having 4 critical points is that one can encode information in principle in superpositions of those of pairs of those points, those critical points, where small fluctuations in the charge or voltage or the flux are rejected at linear order. So the next thing to ask about is what happens if I add realistic parasitic capacitance across the junction or inductance associated with the loop. And very briefly, what I get is something that looks almost exactly the same as before, except now the Hilbert space for this device is the Hilbert space of the Josephson Junction quasi quantum phase slip device tensored with the Hilbert space of a harmonic oscillator associated with the LC circuit. So the L and the C form a harmonic oscillator. And so it turns out that one can partially diagonalize the Hamiltonian for this circuit. And by partially, I mean that K and phi turn out still to be exact quantum numbers, but the component associated with the excitations of the LC circuit are now anharmonic and not exactly diagonalizable. The short version of that story is that I can still characterize the eigenenergies by K and phi, but also by a new quantum number, an integer, which tells me what excitation number is in the harmonic oscillator component of the device. But with respect to any harmonic oscillator excitation 0 or 1 or 2 or higher integers, I have a band associated to that oscillator excitation number. So the lowest band is this picture here, and the next excited band is this picture here. So the lowest band you can still see has a minimum at the center, a maximum at the corner, and 2 saddle points. And those properties are exact. So they're not approximations. That's a statement that's precise. And the first excited band still has saddle points, has critical points at the same locations, but now they're exchanged. So at the center of the band is a maximum. At the corner of the band, there's a minimum. And at these 2 points, there's a saddle point. So you can think of this as a stack of energy bands. Here's the lowest band down here with a minimum at the center. Here's the next excited band with a maximum at the center and minima at the corners. And the transition between these 2 bands happens at a frequency that's approximately 1 root LC, the harmonic oscillator frequency. So you should think of this as a stack of energy bands that have the property that that all of them have extremal points at those 4 coordinates in the band structure. And because they've got extremal points at those 4 coordinates, it still remains true that if I form superpositions of, say, the ground state and one of these other 3 states in the lowest band, the system will reject noise at linear order. The energy changes quadratically in both the quasi-charge and the quasi-flux for small fluctuations around any of those red dots. So even when I add parasitic elements, I have a system that rejects noise at linear order. And so that's the Dualmon. So it's a new doubly nonlinear device. That is, it's nonlinear in both the charge and the flux. It's exactly diagonalizable. And it has these special points, these critical points, where the gradient of the energy landscape vanishes. And at those points, dephasing is rejected at linear order. And so there's various questions that one can ask. How do you do gates on this kind of thing? How do you lock the system to those points, etc. But I want to take a step back, and this won't take terribly long. But in light of this argument that the superconducting phase is not compact, we really should revisit the transmon and see what happens in that picture. So here's the transmon story. To reiterate again. So now I'm thinking about a transmon as being described by a compact phase with a superconducting Josephson Junction term and a charge bias. And here's the spectrum as a function of the charge bias. That is, as I tune the charge bias, I tune the relative energy of the ground state to the first excited state. And this is in a limit, I think, where EJ over EC is about 1 in this particular case. And if I make EJ over EC larger than that, then I'll remind you that the lowest band and the next excited band become increasingly flat, and so they become relatively insensitive to NB. But what do people who build transmons, how do they encode qubits? Well, they say that the lowest state, the ground state is going to be their 0 encoded state, and their first excited state is going to be their 1 encoded state. And so you have a discrete Hilbert space, an anharmonic spectrum that is available for encoding quantum information. So that's the standard story. And if you make those bands very flat, then it rejects charge noise at linear order. That's nice. But there remains always a problem that those two states, 0 and 1, are connected by a dipole transition element. And so there's always a relaxation rate from the excited state down to the ground state. And so that's going to result in intrinsic relaxation and therefore decoherence that one is always subject to. But I just went through this entire argument to say that, well, that Hamiltonian shouldn't be thought of as acting on a compact phase and discrete charge, but should be thought of as acting on a phase that occupies entire real line and a charge that is a real number. And if I do that, remember that this parameter NB turns into a quasi-charge kappa. And so now I've drawn more or less the same spectrum. It's at a different value of EJ over EK. But what I've drawn now is the same kind of spectrum, where now the horizontal axis is not an external control parameter NB. It's the quasi-momentum that encodes, that corresponds to the quantum number associated to the periodicity of the non-compact phase on the real line. And so I have, for a transmon, I have the spectrum associated with kappa equals 0. It's a discrete spectrum. But I also have a spectrum associated with every other value of kappa in the interval -0.5 to +0.5, which are also, at any given value of kappa, a discrete spectrum, but collectively form bands. So I have a band of energies down here. I have another band of energies up here, and I have another band of energies up here, etc. The standard band structure picture you learn in tight binding models and so on when you do Ashcroft and Merman type solid state physics. And so that is not just a representation of the spectrum, but it tells me that the Hilbert space is much, much bigger. I don't have a discrete Hilbert space of well-spaced spectral points. I have bands of eigenstates that are characterized by both a quantum number kappa, the quasi-charge, and also a band index B that labels where I sit in this hierarchy. And just to show you what those states look like, the state at the center of the ground band is this function of phi. Now I'm representing phi as being over the real numbers, but I've plotted it from -2 pi to +2 pi. And you can see that the eigenstate associated with this lowest energy is this comb-like structure. The combs aren't very sharp, but nonetheless, it's a repeating structure with peaks at integer multiples of 2 pi. And at the edge of the Brillouin zone in this lowest ground band, the eigenstate in the phase basis looks somewhat similar. It's a collection of peaks and troughs at integer multiples of 2 pi. But you can see these two states are orthogonal to each other. They've got opposite symmetry with respect to 2 pi translations. And so if I form in a product of those two, I'll get 0. So they're orthogonal states, and they're therefore different states in the spectrum. And just to illustrate that orthogonality again for these two states in the first excited band, at the center of the Brillouin zone, I've got a 2 pi periodic function that oscillates in phi. And at the edge of the Brillouin zone, I have this other function, which is now 4 pi periodic. And you can see that these two are also orthogonal. Likewise, these two are orthogonal, and these two are orthogonal, these are etc. So you can in your head convince yourself that all of those, the four states that I've drawn there are orthogonal states, and that's a consequence of Bloch's theorem. Of course, there are a continuum of states in each of these bands in between those, which are a bit harder to represent because the wave functions are necessarily complex. At these particular points, the wave function is a real number. Okay, and so that fact that I've got this much broader set of states available to me in the Hilbert space means that I could take a different encoding. So rather than encoding a qubit in this state and this state, as is done for conventional transmon, I could think about encoding a qubit in the same ground state, but also in the ground band at the edge of the Brillouin zone. So here's a different encoding, a Bloch encoded transmon, in which I want to think about superpositions of this state and this state at different values of kappa. So I'm going to define a qubit Hilbert space, subspace of the entire spectrum, which has kappa equals 0 and kappa equals 1/2. They're 2 points on this spectrum. And if it's a little bit hard to see because this band is so flat, but in this picture over here, you can see that at the center and the edge of the Brillouin zone, is a general theorem actually, the eigenstates have 0 gradient with respect to the quasi-charge. So at these 2 points, the bands are flat and they must therefore reject charge noise in the same way that I described for the dual mon at the critical points. And there's a symmetry in Bloch's theorem essentially that says that there is no dipole moment between these two states. So the charge operator, that there's no charge matrix element that connects this state with this state, and so there's no relaxation. That is, if the symmetry is conserved, if it's a good symmetry, the 2-pi periodic symmetry of the Hamiltonian is a good symmetry, then there's no relaxation between two states in the same band. There is still, of course, relaxation from up here down to here, or from this state down to here, but there is no transition between these two states. Even though they're not degenerate, they're distinct energies, there's no matrix element in the charge operator that connects them. Okay, so that tells you that actually this is sort of, I think, one of the most interesting consequences of this work is that there's a much bigger Hilbert space in which to encode information, and why don't we take advantage of that? So the first question to ask is, well, if there's no relaxation between those elements, that means they're not coupled by the charge operator or anything that respects the symmetry of cos 2 pi phi, of cos phi, how do I couple them at all? Well, the only way to couple anything is by breaking the symmetry that protects them. So there's 2 ways that I can do that, and I'll just describe them extremely quickly. So on the left here, I've got the transmon circuit, a capacitor and a Josephson junction, and I want to think about shunting an inductive element by switching that inductive element in and out of the circuit. So at some early times, the switch is open. At some later time, some intermediate times, the switch is closed, and then I open the switch again. And there's 2 very simple ways to break that 2-pi periodicity, at least in theory. And the first way is to add a quadratic term, phi squared, which is just the Hamiltonian of an inductor. So if I replace this shunt by whoops. There we go. If I replace this linear inductor by if I put a linear inductor across there, then I end up with this term phi squared in the Hamiltonian, and that manifestly breaks the cos. So that manifestly breaks the cos phi, the 2-pi periodicity associated with cos phi. So if I hold that inductor across the circuit for some period of time, the system evolves in the global Hilbert space. And when I open the switch again, I can ask, what does the state look like? So in these pictures here, these colorful pictures, I'm representing the state of the system in the Zach basis. This is the K phi basis, which is characterized by K being in a compact domain at the quantum number K in a compact domain, and the quasi flux phi also in a compact domain. but it corresponds to a system in which the flux or the charge themselves are non-compact operators. And so let me very briefly say, I want to initialize the system in a state that's localized around k equals 0. That's this ground state down here. That's this state down here. And I'm going to switch an inductor across that transmon for varying periods of time. And I'm going to denominate that hold time in units of a quantity T2 pi. That's roughly speaking this energy scale here. If I hold that inductive element across the circuit for this time, T2 pi, the system goes from its initial state to a state that's very much like the initial state. If I hold it for half of that time, the system goes from the initial state to one which is localized near k equals 0 to one which is localized near k equals a half. And if I hold it for a quarter of that time, I end up in a state which is a superposition of those two configurations, one that's localized near k equals 0 and another that's localized near k equals a half. And I can plot now as a function of the hold time, the population of the system to be in its initial state, which is this red line that goes from 1 down to near 0 and then back up to nearly 1 at this time, T2 pi. And I can plot the probability for the system to go from its initial state to be in this intermediate state here, which goes from 0 up to some large number and then back down again. And at this point here, which is this roughly this quarter of a period, I'm in a superposition of the two states, one near quasi-charge equals 0 and one near quasi-charge equals a half. So that's conceptually the easiest thing I can do. I can shunt a linear inductor across. The next thing I can do is to shunt a device which is theoretically much easier to treat for some very specific. I see I've got to finish up. Sorry. Let me skip over this very briefly. It's a way to use a 4 pi periodic gate to break the 2 pi periodic symmetry, and suffice to say that one can produce gates that look very much better. There's a point in which I'm in a superposition of the k equals 0 and k equals a half state, and so I can conclude there just by saying that the system is this new encoding, the Bloch encoding, is an extremely robust one in which it rejects noise at linear order, and it's an exact property for the dualmon and the transmon both, that they reject charge noise in these states which are superpositions of points at the center and the edge of the Brillouin zone. And the reason that those states are allowed is because the Hilbert space is very, very much bigger than would be suggested by one in which the charge or the flux are compact coordinates. Gates are conceptually straightforward to write down, but experimentally maybe a bit tricky. And there's a bunch of work that we're working on right now around how to manage or deal with quasi-particles and so on. But so what I want to conclude with is this observation that even transmons, which are now the workhorse of superconducting qubit land, have a much bigger Hilbert space where perhaps we can do something more interesting in terms of encoding qubits. So I'll end there. Thanks very much.
I'll stop.
All right. All right. So are there any questions from people in the audience?
Since I'm already unmuted, I'll ask one. Is it too soon to think about some of these other challenges, like things like the number of control wires that you have to stick into a fridge? Are there differences there in sort of these practical problems that come up with?
I think in a very broad picture, yes. I guess one takeaway message from this work is that the encoding in Bloch states of either the dualmon or the transmon are ways to suppress noise at linear order. So there's a passive suppression of noise just because you're operating at these special points where the gradient of the energy landscape vanishes. So what does that tell you? It means that you can spend less effort, one would hope, on noise mitigation and error correction. That is, you have intrinsically quieter qubits. So maybe operating at the center and the edge of the Brillouin zone, let's say for the sake of argument, gave you a factor of 10 reduction in dephasing because you've suppressed relaxation entirely. So that's a passive gain that that qubit enjoys by virtue of its operating at these critical points. There's some more work I've started recently to build in some classical control theory, where the idea would be that you have a local classical control protocol that's locking the system to the special points. And that might get you another factor of 10 improvement just using classical noise suppression from control theory. And so maybe, I mean, the hope would be that when you put together passive and active techniques for noise mitigation in this device, either of these devices, you end up getting a gain of maybe a factor of 100 in the performance of the hardware qubits you have, which means that you can spend a lot less effort and resources on encoding into complicated error correcting codes. Of course, you still have to do that because none of the things I've described give you fault tolerance. They just give you intrinsically quieter qubits. And so the hope would be that you can indeed do what you want, Chris, which is reduce the number of control lines by virtue of the fact that you've had to spend vastly less effort in active qubit error correction because you've found ways to get several orders of magnitude improvement in the performance of each physical device that you're working with.
Thanks, Tom.
Of course,
Any
at
other
some
questions?
point you need to have control lines, just like you do in your computer. You've got control lines that address the RAM and so on. It's just that in digital computers, you spend very little effort on error correction because the actual hardware is already very good.
Right.
Tom, in kind of the naive picture that I normally have of thinking about our transmons, with this bias voltage, we have this external parameter that it's noisy, and there are these points that are basically locally flat, but this is a parameter that can really wander around via some sort of diffusion, and it goes across this entire spectrum. How does this behavior look like in these quasi-charge variables? Do you still see a noise that kind of wanders around that can really diffuse from one of these, say the trough all the way up to the peak, just sort of randomly?
Absolutely. So that would be a problem that, as I said, well, I guess the way to say it is that the passive noise rejection that this encoding, Bloch encoding enjoys protects against small perturbations in this external charge noise, but large excursions that might happen by some diffusive process are not protected. So in terms of timescales, I guess what you'd say is that the passive noise rejection, by virtue of the flatness of the band at those two, excuse me, too much talking. The passive noise rejection you get by virtue of the flatness of those bands rejects fast noise at short times, but it doesn't deal with large drifts over longer times. And so that's what I was hinting at when I was talking about some active processes that we're working on now. Okay, so that's where the classical control comes in to try to keep them locked to these specific bands. That's it. These areas on the bands, right? Yeah. Okay. Any other questions? Well, look, I think in view of the time, that's a good place to wrap up. Thanks very much for joining us, Tom. That was a really great talk, and we'll catch you again soon. Yep. Thanks everyone.